In the previous two videos, we solved for expressions in our complicated work energy problem. For this one, we're just going to put some numbers to it and work it out and see how that works. So the numbers I've chosen are the mass of the block will be 5 kilograms, the plane is inclined at 32 degrees, coefficient of kinetic friction is 0.1, our spring has a constant of 150 newtons per meter, and we'll start out 2.5 meters above the equilibrium position of the spring. So the next thing I've written is just the expression that I got in the first part of this problem, the expression for, it's a quadratic equation in delta x that I said you could solve quadratically. So taking the values that I've put here, I've put them in, and I've gotten these values, 1.53 units if you work them out are 1 over meters, negative 0.445, there are no units here, and 2.1 meters. So the units are important. Notice I'm adding these terms, which means they all have to have the same units. I've got meters squared buried inside here. I've got a meter buried inside here. I've got no dimensions over here. So this has to give me a 1 over meter. This has to be dimensionless, and this has to give me a unit of a meter. So all of my terms end up with units of meters. That's the only way I can add them together. Okay, so this is the expression that I've come up with. 1.53, 1 over meters times delta x squared minus 0.445 delta x minus 2.1 meters, which is the quadratic formula. To be honest, I just plugged this into Wolfram Alpha and told it to solve it. Of course, you can solve it by hand if you're so inclined, and you just love solving the quadratic formula. I, however, do not. So I just told Wolfram Alpha to do it for me, and this is what I got. Negative 1.04 meters or 1.33 meters. Recall there are going to be two solutions to every quadratic equation. I'm going to pick the positive root for lots of reasons. We're always going to pick the positive root. One good reason, you can think of it like this. Moving down the ramp I've defined as positive. Remember, my friction force was up the ramp. I said it was negative. So the spring is compressing down the ramp, and so I'm going to pick the positive root of this to compress down the ramp. And so I'm going to pick 1.33 meters. And that's the numerical answer to the first part of this question, 1.33 meters. For the second part, I want to know how far back up the ramp it moves from the equilibrium point of the spring. So I just listed my expectations. The final height will be less than the original height because of losses, which means, of course, the distance it moves up the ramp will be less than the original distance it moved down the ramp because of losses. So just as a sanity check, I've calculated what that distance it moved down the ramp was. 2.5 meters, its original height, divided by the sine of the angle. Run through the trig if you need to here. That gets me a total travel distance of 4.7 meters, and that's before it hit the spring. That's the distance from the initial position to the equilibrium point where I was told to measure from. And so here's my energy equation. I've got to account for everything. I'm solving this in one step, remember. This is confusing, go back and watch the second video. Initial kinetic energy 0, final kinetic energy 0, because I'm at rest when I start, and at rest when I stop. Notice the final spring potential energy is also 0. I'm not even touching the spring when I stop. And don't forget the work done from non-conservative forces is friction still, so this is going to be a loss, right? If I had some force like a rocket booster on this thing, this would be a positive, this would be a gain in energy, but there's a negative sign buried in here because this is a loss. So if I unpack all that stuff, I get this long expression, 1/2 k delta x squared from the spring potential, minus mg delta x sine theta from the original gravitational potential. Remember, it's negative because I'm below my 0 point. Minus mu k mg cosine theta is the work done from friction times this distance, I should say, df plus delta x, final length up, final distance up the ramp plus whatever that compression distance was. And that's got to be equal to the final potential gravitational energy, mgh final. So my next step, just to go through the algebra, I'm going to get hf in terms of df by multiplying it by sine theta. I'm going to divide every term by mg because I've got an mg in most of my terms. So when I do that, I come up with this expression. The mg is now in the denominator of my spring potential energy term. It's disappeared from all the other ones. And what's left is to combine like terms and do some factoring. So I'm going to get df to the other side here. and factor it out, which I've done here. df sine theta plus mu k cosine theta. I've got a delta x here, I've got a delta x here. So as I'm moving all this stuff around, I'm going to factor that out at some point. In this step, I solved for df. It's equal to this stuff divided by this factor. And here, I'm going to factor out the delta x here. And what I get is this term minus delta x times sine theta plus mu k cosine theta, which is the same term I have in the denominator. So I'm going to cancel it out from this term. And what I have left is this. K delta x squared over 2mg times sine theta plus mu k cosine theta minus delta x. Remember, from this term, the only thing I have left is a delta x. First term, I have all of this stuff. When I plug in numbers to this, what I get is 3.07 meters, which means it moves up the ramp 3.07 meters from the equilibrium position of the spring. So let me check myself. I expect that to be less than my distance I came down. The distance I came down is 4.7. 3.07 is less than that. I feel good about that result. It's less than that because of the frictional losses. All right, I hope this made sense. You should solve this problem at least 3 or 4 times until you understand it.